If you spend an hour pacing back and forth in your room, you'll feel physically exhausted, even though you've returned to the exact spot where you started. You've put in significant effort, but in a geometric sense, you haven't actually gone anywhere. We track effort as distance, a scalar quantity of ground covered that only goes up. Physics requires a second metric, displacement. This vector is defined by how far you moved and your direction. When you return to the start, displacement zeroes out. This shift in thinking began with Galileo Galilei. He realized that to understand motion, you have to look past the push and the friction of the world and treat position as a mathematical state on a grid. By separating the scalar, the total effort, from the vector, the specific change in space, scientists can predict exactly where an object will be, rather than just how much energy it used up. Take a car moving down a straight road. The speedometer gives you a single number, like 60 kilometers per hour. That is your speed, a scalar that ignores your heading. But velocity is the vector. It's the combination of that 60 kilometers per hour and the direction the wheels are pointed. If the car turns, even if the speed stays the same, the velocity is changing. We've calculated these rates for centuries. The 14th century Indian text Ganita Kamudi used distance divided by time to solve problems of messengers traveling toward each other. Speed tells you how fast you're going, but velocity tells you where you're headed. For physics, the where is the part that matters. We can visualize this change on a graph. On a position time graph, a steep line represents a high velocity, while a shallow line represents a slow one. The slope literally is the velocity. Switching the vertical axis to measure velocity, slamming the brakes becomes a downward slope. This slope shows acceleration. The rate velocity is lost. As a truck stops suddenly in front of you, you must know the exact ground covered before a complete halt. That stopping distance is the geometric area beneath this slope. It's made of two parts, a rectangle representing initial speed over time, and a triangle representing velocity lost while braking. To find total distance, add the rectangle and triangle areas. The rectangle is initial velocity u times time. The triangle's height is acceleration times time, giving 1/2 a times t squared. Together, they form the kinematic equation for displacement. This area calculation determines whether you stop in time or collide. It's not just math, it's the physical space the car is required to occupy while it sheds its velocity. Circular motion is a unique application of these rules. Imagine an object moving in a circle at a perfectly steady speed. In a turning car, you feel pushed against the side of the door. You're feeling acceleration, even if your speedometer hasn't moved a single digit. Because velocity includes direction, any turn is a change in velocity. On a circular path, the direction is shifting every single millisecond. That constant change in direction means the object is perpetually accelerating toward the center of the circle. According to Newton's first law, an object wants to keep moving in a straight line. If the force pulling it inward disappears, the object immediately follows its final velocity vector, traveling away from the circle in a straight line. From pacing in a room to orbiting a planet, motion follows a consistent geometric map. By tracking both magnitude and direction, we can calculate the exact path an object must take through the world.